Boosting. Boosting uses slightly different technique when compared to bagging. Boosting is also one of the most famous ensemble method. Boosting is a well-proven theory and it works really well on many of the machine learning problems like speech recognition. If bagging is wisdom of crowds, then boosting is also wisdom of crowds, where each individual is given some weight based on their expertise. Boosting in general decreases the bias error and builds strong predictive models. Boosting is an iterative technique. We adjust the weights of the observations based on their previous classification. If an observation was classified incorrectly, then boosting tries to increase its weight of that observation, and then later on that observation will be given more weight, and then it will be classified correctly later on. The boosting main idea here is the idea that overall philosophy of boosting. Take a random sample first of the population of size n. Each record has 1 by n chance of picking. So let 1 by n be the weight of each observation point, that is w. Weight is w. So we first take a random sample from the population. Now we build a classifier on that. Note down the accuracy. Obviously the classifier may not classify all the records correctly, some of them are wrong. Now take a weighted sample this time. Next time what we do, we take a weighted sample. Whatever was previously misclassified, we will give more weight to that misclassified observations, and then this time we will pick them. So in this new weighted sample, the previously misclassified observations will be picked more often. Build a new model on the reweighted sample that we just collected. So in this new model, definitely most of the previously wrongly classified values will be picked up. Since we picked many previously misclassified records, we expect this model to build a better model for those records. Again, for this new model, check the error. If the classifier still misclassifies some of the records, then we repeat the same procedure. Again, you take a new random sample, but this time when you are taking a random sample, whatever was misclassified by the previous model, give them more weight. Make sure that those values are picked more often than the ones that were already classified correctly. Then take that particular sample, try to build a model on that particular weighted model, and the final classifier is nothing but accuracy into each of the classifications. So for each model, whatever was the accuracy, we will, based on that, we will consolidate all these models together based on their accuracy. That is the boosting main idea. So what is the boosting main idea? Initially we have same weight for each of the, so we just pick one sample, or it may be just whole population. We build a model directly. Once we build a model, then there might be some error. That means there is an accuracy factor of alpha 1 for this particular model. This model has an accuracy of alpha 1. Now we update the weight. That means we resample again. From this sample we will take a weighted sample. How do we take the weighted sample? Whatever was misclassified earlier will be picked more often. Whatever was classified correctly will be chosen less. Then we build a new model C2. It has an error of alpha 1. The accuracy is it has an error of epsilon 1, epsilon 2. The accuracy is alpha 2. Again, here whatever is misclassified, that will be picked more often from this one. Within this sample, again the new weighted sample will be picked. If we are reiterating, again the misclassified observations will be picked more often. The correctly classified observations will be picked less. We repeat the same process until we achieve the desired accuracy. So how weighted samples are taken? This is a detailed explanation. Imagine a data with 10 points, 1, 2, 3, 4, 5 and 10. And what are their classes? Actual classes, minus, minus, plus, plus. So these are the actual classes. Now we build model M1 and the predicted classes are, so minus is predicted as minus, so correct. Minus is predicted minus, it is correct. Here plus is predicted as minus, so model M1 is classifying wrongly the third observation. Fourth observation predicted wrongly. Sixth observation predicted wrongly. All the other observations are predicted correctly. Now we take a weighted sample. 3, 4, 6. These observations are predicted wrongly by previous model. So we have to give more weight to them. In this weighted sample, 3, 4, 6 will appear more often than others. 1, 2 is picked, 3, 4 is picked, 5 is also picked, 6 is picked, 7 is picked, again 4 is picked because 4 was misclassified, 3 is picked, 6 is picked. So each of these are picked twice. Again we build, so these are the actual classes for 3, 4, 6. Yeah, earlier 3, 4, 6, these are the actual classes, these are the actual classes for 3, 4, 6, and again we build a model M2 on this new data set. M2 is classifying everything like previously misclassified ones are classified correctly now, 3, 4, 6 are classified correctly, but 5 is misclassified, minus is classified as plus, minus is classified as plus, so these two are misclassified. So we need to repeat the weighted sampling once again. So this time we will give more weightage to 5 and 7 because they were previously misclassified in the weighted sample. New weighted sample, they will be picked more often. 5 is chosen 3 times, 7 is chosen 3 times, remaining all the observations only 4 times we have picked, 6, 3, 4, 6. Now in this model, these are the actual classes, this is the predicted class, and we can see the model M3 predicts everything correctly. That is how weighted sampling and boosting works. To understand boosting clearly, now we will see a visual illustration of the same example that we discussed in boosting earlier. Now take a look at the data observation point numbers, record numbers, because in boosting the sampling and weighted sampling, we need to remember the records. What exactly is the observation number, because it will be picked later based on whether it is classified correctly or wrongly. So these are the 10 data points. Some of them are positive, some of them are negative. You can see that in the illustration here. So here there are 5 positive points blue, 5 negative points red, right? 1, 2, 3, 4, 5, these are the points. So you can directly see the points here, first point, second point, and 3, 4, all these are the points. Now what happened? We build the model M1. This is the classifier M1 that we have built. 3 out of 10 are misclassified by model M1. What are they? 3, 4 and 6. These are misclassified by model M1. These, so as per boosting technique, these will be resampled again. Next time we will give more weight to these points. So here 3, 4, 6 are misclassified. These are misclassified. Obviously you can see anything above this is classified as red, anything below this line is classified as blue. These two are correctly classified, these are all correctly classified, these are wrongly classified. This is model M1. So this is sampling, first sample, this is model M1 result. Now we will resample, give more weight to these data points, and then build a model M2. So we resample, so each one of them is picked more often than other ones, so other two are not even picked. So there is 1, 2, 3, 4 points, and these are 6 times, so 3, 4, 6, 3, 4, 6 is picked again. Now model M2 is built. This is model M2. So model M2 is misclassifying some points. Model M2 is saying that anything above this is red, anything below this is blue, so these 2 points are misclassified. These are classified as blue but they are red. So this is the classification line by M2. This was M1, the old one. This is M2. M2 is misclassifying these two wrongly, that is 0.5 and 0.7. These two are the ones, they are actually minus, they are classified as positive. But model M2 made sure that these 3, 4 and 6, these data points are classified correctly. They are positive, they are now classified as positive. Since from the previous model, this model has an improvement. This has classified these points correctly. But again, this model has misclassified these 2 points. What do we need to do? In the next iteration, we have to pick these 2 points more often than usual. So 0.5 and 0.7 will be, observation 0.5, observation 0.7 will be picked more often than other ones. That means they will be given more weight. So this is the final, this is the third weighted sample, in that these 3 are picked, 6, 3, 4, these 3 are picked, and 5, 5, 5. 5 is picked thrice, 7 is picked thrice, so they are picked, given more weight. Now we build a new model M3 that has correctly classified everything. On the right hand side is red and on the left hand side is blue. So model M3 has classified everything correctly. M3 is built on this data. Anything above right side line is plus, anything on the other side of the line is negative. So M3 has classified everything correctly. Now everything is classified correctly, we don't need to do further weighted sampling or anything. So we built 3 models, so that is M1, M2, this is M2 and M3. So 3 models together are giving the final result, and the final model will be now picked on based on weights for a given data point. More than 2 models seem to be indicating the right class. If you see, let's say this point, if you take point 1, the actual is plus. M1 is classifying it as plus only. M2 okay, the actual point here for 1 is minus. M1 is classifying it as plus, so that is wrong. So let's take an example of this point 6. For example, for data point 6, it is classified as minus by M1 because anything above the line is minus, anything below the line is plus for M1. So that point 6 is classified as minus by M1, whereas M2 is classifying it as plus, whereas M3 is classifying it as plus. So final result will be plus. Similarly, we take point 2, that is over here, that is classified as minus by M1, whereas M2 and M3 final result will be, M2 and M3 are classified as minus, final result will be minus. So final weighted combination of all 3 models and the predictions will yield a very accurate model. So that is how boosting works. So we build model and then the misclassified points will be picked up once again to make the model better, and final model will have a weighted, final model will be a weighted model based on the accuracy of the all individual models that we built till now. Now the theory behind the boosting algorithm, we would like to skip this one. The whole, I mean, we just saw the visual illustration, but there is a whole lot of theory, exactly how boosting works, how the weighting are done, how the sample weights are created. There is something called an intermediate factor alpha that is almost analogous to accuracy rate of the model. Based on the accuracy rate, next weight will be chosen, the samples will be chosen, the weights will be updated, and the models will be built. And the final model is also created based on the each individual model accuracy factors, and it will be multiplied with the actual classifiers. So there is a proper scientific method behind finally arriving at the bootstrap, arriving at the boosting algorithm results. There are 2 types of boosting: ADA boosting, that is also known as adaptive boosting. Till now we discussed adaptive boosting techniques. Here we give high weight to misclassified records. There is something called gradient boosting. It is similar to ADA boosting. The approach is same, but there is slight modification during the re-weighted sampling. There are, while doing the weightages, there will be slight difference, but the overall philosophy is same. Only the weighting criteria will be changed. We update the weights based on the misclassification rate and gradient. So gradient boosting serves better for some class of problems like regression, whereas overall boosting technique is what we discussed till now. Let's see a lab an exercise to understand the overall boosting algorithm. Let's do an exercise on the real data to understand the boosting algorithm. The objective is to do the e-commerce products classification, basically rightly categorizing the items based on their detailed feature specification. There are more than 100 specifications that have been collected. We need to classify those products. So the data set is products. I mean, what type of product is that we need to classify that. The data set is e-commerce product menu, the training data set. First we will build a decision tree model, check the training and testing accuracy. Then we will build a boosting model. We'll see what is the accuracy of the boosting model on the training and testing data, and we will see whether there is an improvement from the earlier model compared to decision tree, whether boosting tree is better or not. Here is the training and testing data. So we are importing the products menu data. There are 50,000 observations and 102 features in 102 variables in the training data, whereas there are 11,756 observations and 102 columns in the test data. So we can have a quick look at the training data. The training data has specification 1, specification 2. First one is ID, and the last one is again specification. We can see that data set, it has 99, so we can see only 99 columns here. We can see the names as the names of training data. The last one is category. Let's see the head of training data. So the last one is category, whether it is mobiles or whatever is the type of category class that belongs to. Based on the specifications, we need to classify it in the e-commerce website automatically. That is the overall problem statement. So we'll try to build a decision tree model. We'll try to predict the category by using the specifications, and we will build our first decision tree model on it. Data set is fairly large, it might take some time. Then we will build, we can see the plot as well. This is the decision tree model, and we will try to see the confusion matrix to understand what is the accuracy. The accuracy is 60%, very less on the training data itself. On the testing data, not sure how much it will be. It will again 60% on the testing data. So that is what a decision tree can do. So even in the confusion matrix, you can see many of the accessories are classified as appliances, etc. So there are a lot of errors. So there are too many points that are above and below the diagonal element where the confusion matrix, it is very clear that our predictions are going very wrong. Now we will go to boosting. We'll try to do boosting technique. We will first, boosting algorithm is about building a model, and whatever is misclassified, it will again take that misclassified one with a higher probability, or the sample will be choosing those misclassified observations more than other ones, and then finally try to classify it correctly. So let us see what boosting classification can do. We'll include some important libraries that will be used later on, and then we will convert the data sets to numeric format, because the function that we are going to use is xgboost. Xgboost and xgboost needs at least one numeric column, so we are converting our values to numericals. That is not going to be a big problem. And then we have to convert the data set as matrix, because xgboost accepts matrix format only. So we can't give a data frame directly as an input. We have to convert the test and training data as matrix. So we are creating train matrix and test matrix. So we are creating two matrices here, and then we need to label should be numeric format, and it should start from 0. So that's why we are creating the labels here from the, so that is the y variable, that is the output variable, the outcome. We are creating the outcome. Basically we are preparing the data for analysis. So this is the outcome, we just created it. And then now we are creating the parameters, list of parameters. So we have to give objective a function, and then multi softmax, set xgboost to multiple classification. This is multiple classification, number of classes are 9, and the error multi-class error rate is based on what xgboost will calculate the error rate to calculate the misclassification error, etc. So these are the parameters that we need to set to start with, to get started with XGBoost model. So we need to give multi softmax, which is set XGBoost to multiple multi-class classification using the softmax objective. You also need to set the number of classes. So how many number of classes are there? There are 9 different classes. We can get it by looking at the number of different classes in our objective variable. So library is XGBoost and the model is XGBoost. Number of parameters, we have given the parameters already, we have set the parameters. Data is in terms of matrix, training matrix. Label is Y, we have created that numeric one. 40 rounds of weighting and reweighting we are doing. Whenever there is an error, it will again see it boosting. You can, if you keep on increasing the iterations, you might get a model that will be totally error free, but whether it will be robust enough, whether it will work on the testing data or not, is what we need to see. So that's why the number of rounds, number of iterations, we can choose to be 40, or you can increase or decrease based on the accuracy that you are getting. So we'll build the XGBoost model. So first iteration the error is 26%, second iteration 24%. Slowly while iterations are increasing, the error is reducing. Final iteration error is 13%. So the training accuracy is around let us calculate the training accuracy for boosting model. Training accuracy is 86%. We can see the error was around 13%, 13.9. that's why training accuracy is 86%. Accuracy on the test data, that is what matters a lot. Accuracy on the test data is 80%, which is much better than our earlier model, that was decision tree model, which gave 60% accuracy. That is how boosting works. If you want to compare the boosting versus random forest, we can build the random forest model on the same data set. Let us see what is the training accuracy. So boosting gave a testing accuracy of 80%. So overall our accuracy is 80%. Let us see what does random forest give. The data set is large, that's why random forest takes some time to build all these 50 trees. So this is the random forest with a training error of 89%, accuracy of 80%. Testing accuracy, let us see. So testing data, it has an accuracy of 80%, whereas boosting has an accuracy of almost same on the testing data. On the testing data, boosting again performs 80%, and random forest also, another ensemble technique, performs 80%. So boosting is as strong as random forest, and in some cases it works better than random forest. In fact, if we play around with the parameters like iterations and all that, we might see a better model. So I'm increasing the number of iterations. That will definitely increase the training accuracy for sure. So we started with some training accuracy. If I increase number in each iteration, the error is reducing. The training accuracy is definitely increasing here. So now the training accuracy is 87%. Now what is the testing accuracy, the one that matters? It is again not much change. So boosting finally shows an accuracy of 80%, which is much better than any straightforward model like decision tree, which gave 60% accuracy, and random forest gave 80% accuracy. This is how boosting works. Till now we have seen most of the ensemble techniques. They are working better than the individual models. When ensemble technique doesn't work, when ensemble models doesn't work, I mean they don't work better than individual models. The models in the ensemble, I mean the consolidated ensemble model, all the individual models need to be independent. We can't build the same model multiple times and they expect our final error rate to be reduced. We may have to bring in the independence by choosing subset of the data, by bootstrapping sampling, or subset of the features while building the individual models. Ensemble may backfire if we use dependent models that are already less accurate. I mean, if they are already less accurate, the final model might even turn out to be a worse one. Yes, there is a small disclaimer in the wisdom of crowds theory. We need good independent individuals. If we collate any dependent individuals with poor knowledge, then we might end up with an even worse ensemble. For example, we built 3 models, model 1, model 2 and model 3. Model 1 and 2 are very bad. Model 3 is a good one. Most of the times ensemble will result the combined output of model 1 and model 2 because they are dependent and they are bad. Based on voting, the result of model 1 and model 2 will be the final. Even though model 3 is good, it will not be considered. So our final ensemble will be a first one. That's why we need to be careful. Ensemble technique, all the models need to be independent. We need to be careful while and make sure that independence is satisfied. Independence criteria is satisfied. So let's see the conclusion of this whole ensembling technique session. Ensemble methods are most widely used these days. Many people are using because the computation power and the advanced machines, it's really not a huge task to build multiple models nowadays. Very quickly we can build many models, many iterations. Both bagging and boosting does a good job of reducing the bias and variance. Most of the people are using them. Random forests are really fast since we are building many small trees. It doesn't put a lot of pressure on the computing machine. Random forest can also give variable importance. At the end of the random forest we can get the a matrix with variable importance. We need to be careful with categorical features. Random forests tend to give higher importance to variable with higher number of levels. In boosted algorithms, we may have to restrict the number of iterations to avoid the overfitting. The more iterations you give, definitely boosting algorithm will reduce the error, but what really matters is testing error. So avoid overfitting, choose the optimal number of iterations in boosting algorithm. Ensemble models are final effort of data scientists. So finally we come to ensemble models. We first build the initial models, individual models to get an idea, then we collate multiple models to build the ensemble models. While building the most suitable predictive model, we finally choose the ensemble model, that is a consolidation of multiple independent individual models.